Norton theorems. Let's continue the discussion using Norton theorems to analyze AC steady state analysis. By the way, before I start, okay, I think now it's recording. Yeah, last week we did already explain many of the techniques that can be used for analyze steady state analysis, complex circuit of RLC circuit with AC current, yeah, and then analyze the parameters, some parameters in that circuit, yeah, using a node analysis, using loop analysis, source transformation, superposition, and then Thevenin as well as Norton's. Yeah. Let's see some of the example now. This is, for example, here now we have this circuit and okay. Basically, this is the same circuit as the previous example. Yeah, only. Let's now we skip superposition and transformation. We are asked to find the V output here at the 1 ohm resistor. Okay, so look at the nodes, the choice of the ground over here, and we choose here to be the super node. Then the constraint of the super node will be V1 minus V3 equals to 12 volt with a phase angle of 0 degrees. And from this, you can calculate KCL at the super node. Minus 4 is from this one, because this current source is, the current is going towards the super node. So then we assign it with negative value. Then V3 here minus V0 divided by J1. Yeah, with this one, V3 minus V output. So this one minus J divided by 1. This 1 ohm resistor. Then V3 minus V2, this current, V3 minus V2 divided by 1 also. Then from here, V1 minus V2 here divided by minus J1 or minus J. Then from here, we are left with this part, this current, V3 minus 0, the ground, divided by J. Okay. Then the node, the KCL at the node V2 will be V2 minus V1 divided by minus J minus 2Ix, because the direction of Ix is towards the node, so we assign negative value to it. Then plus V2 minus V3 here divided by 1 ohm equals to 0. Then at this node, yeah, at V output node, KCL at V output, V out divided by 0, the ground divided by 1, plus V out minus V3 divided by 1 ohm also here, plus, since the current source for ampere here is directed outward of the node, so we assign positive value, plus 4 with a phase angle of 0 degree. The controlling variable here, Ex, equals to this one, yeah, using Ohm's law. So we assign Ex equals to, Ix direction is from V3 towards V out. So then Ix equals to V3 minus V out divided by 1 ohm. Yeah. So from here, we obtain then from KCL at V output, we obtain the connection, the relationship V3 equals to 2 V out, yeah, plus 4 volt. And then we have from the supernode constraint V1 minus V3 basically equals to 12. So then we can substitute, we can have these two equations. Okay. V1 equals to V3 plus 12. Then we substitute V3 here with this 2V out plus 4. So this becomes 2V out plus 4 plus 12. 2V out plus 16. Then from here also we obtain V3 minus V output equals to V out plus 4. This we can substitute into this value. So from here, from KCL at V2, we then substitute V1 with 2V out plus 16. So here becomes V2 minus V2, V out minus 16, yeah, times J, because this is already then multiplied by J divided by J. Yeah, so that become J, because J in the denominator, J multiplied by J equals to minus 1. Minus 1 multiplied to minus equals to plus. So this becomes J, V2 minus 2V out minus 16. Minus Ix then we replace with this one, V3 minus V out, and V3 minus V out equals to V out plus 4. Okay, so this becomes minus 2V out plus 4. And finally, this value, we replace V3 with V2 minus, this becomes V2 minus V3, we replace with this equation. So become V3, V2 minus 2V out minus 4 equals to 0. So we have still V2 here. V2, we use the KCL at the super node like this. From here, then we also obtain an equation, yeah, by replacing V3 using this 2V out plus 4 and replacing V1 using this 2V out plus 16. And thus we obtain another equation with two variables, two unknown variables, V2 and minus V2 and V output. So we have now two equations with two unknowns, so we can solve V2 and V output. Yeah. By adding them, then we will obtain V output equals to minus 8 plus 4J divided by 1 plus 2J. This we can multiply by 1 minus 2J. Okay, multiply by 1 minus 2J divided by 1 minus 2J to obtain real and the imaginary part. Yeah. So this is not final. So remember, when you are doing test later, when you are solving this, please solve until you obtain x plus jy. Okay, x plus jy, the form. If you want to express it in as a complex form, or otherwise you can also express it as phasor form. Let's try now using loop analysis instead of using node analysis. So mesh currents are acceptable. So there are 4 mesh currents. Yeah. So from here, the mesh currents are determined by the sources in this one. Yeah. Since there are fixed, yeah, there are current source here, permanent constant current source, 4 ampere with a phase angle of 0. So I2 equals to minus 4. And I3 here also there is one current source here, a dependent current control current source. So I3 equals to 2Ix. Okay. So from mesh 1, then we can derive using the mesh equation using Kirchhoff voltage law like this. So minus J1 minus J times I1 here plus this 12 volt. This is voltage source plus 12 volt plus I1 minus I3 times 1 equals to 0. At mesh 4, then 1 ohm times I4 minus I2 here, plus 1 times I4, plus J here, I4 minus I3 equals to 0. The control variable Ix equals to I4 minus I2. Okay, yeah, this. Then the variable of interest is V output, and V output equals to I4 times 1 ohm here. Okay. And this is what we look. So we have to find the value I4 here. So from here, then since I3 equals to 2Ix, we substitute Ix with I4 minus I2. So we obtain I3 equals to 2 times I4 plus 4. Okay. Yeah, because then we substitute I2 with this -4. Yeah. And there is minus here, so this becomes positive. Then from mesh 4, here we obtain I4. We substitute here then the I2 and I3. I2 we substitute with -4, so this becomes +4. And plus I4, J, I4 minus, and substitute I3 here with 2 I4 plus 4 here. So -2 times I4 plus 4. So we obtain the value of I4 from here. Okay. So simplifying the equation, we will obtain I4 equals to negative 4 minus Hj divided by 2 minus J. So this is not yet final. So the V output, basically this I4 times 1. Okay, and here to simplify, we multiply with J and J. So this then becomes, so let's see, let's try to calculate ourselves. So from here, this become I4 becomes negative 4J minus plus 8, yeah. J times J is negative 1. Negative 1 times negative is positive. This it becomes 2J plus 1. Yeah, basically this one equals to this one. And this is not final yet, so you need to multiply with 1 plus 2J, 1 plus 1 minus 2J, and 1 minus 2J. Okay, if you want to have final value, so this minus 8 plus 4J divided by 1 plus 2J, like this. Okay, and simplify further so that you get then later the real part and the imaginary part. Okay, now let's try using Thevenin's theorem then. The variable of interest is the V output here. Okay, so we need to replace the whole remaining circuit to become a Thevenin equivalent source in series with a Thevenin equivalent resistance. So we have to find the VOC, the V open circuit of the circuit, yeah, at this terminal, between this terminal and this terminal. And then finding the ISC, the I short circuit, and then finding the Thevenin equivalent resistance by dividing the Thevenin equivalent voltage VTH by the ISC, the short circuit current. So first, we try to calculate the open circuit voltage here. Okay, so we have here Ix. You can use the Ix dash here equals if we use mesh current here. So this Ix dash, since this is the same loop, yeah, the same loop. So this equals to the 4 ampere with a phase angle of 0 degree. And then from here, the same loop with this one. So this equals the current flowing through here equals to 2Ix also. Okay. And since Ix is 4 ampere, so this 2Ix equals to 8 ampere with phase angle of 0 degree. Then so then VOC, the V open circuit here, can be calculated from the voltage across this one plus the voltage across this resistor plus the voltage across this inductance. Okay, which then equals to since Ix is towards the right, so, and we calculate using the VOC loop is this one counterclockwise. So the voltage across this 1 ohm equals to minus Ix times 1. Minus Ix is then minus 4 here. Then plus this 2Ix or 8 plus J1, yeah, or Hj volt. Okay, this is the V open circuit. Okay, then the alternative procedure to compute the Thevenin impedance is to set to 0 all independent source. In this case, we can set, yeah, this one short circuited and this one open circuit. And since we have a dependent source here, then we apply an external probe flowing, for example, 1 voltage or 1 ampere to get the current there. Yeah, this is one. So here we short circuit the independent voltage source here. We open circuit the independent current source here. And then we apply external probe here. We apply the voltage at this terminal. Okay. The ZTH, the impedance resistance, or impedance, the equivalent impedance will be equals to the voltage here divided by the IX. Since here IX double dash. Since here the IX double dash flows through this loop. Yeah. So then the impedance voltage, the Thevenin equivalent impedance will be equals to the voltage across this terminal divided by the current flowing through this V test, which is this I double dash X. Okay, and so the I double dash dash here will be equals to the current flowing through this J1 ohm impedance. Yeah, then using Kirchhoff voltage law, the V test equals to here minus Ix double dash times 1 ohm plus J1 ohm times I double dash X. This equals to the since the ZTH equals then to 1 minus J ohm. 1 minus J ohm. Okay. Then from here, then we obtain already the impedance. We obtain the voltage open circuit. Then we make them into series to make them as a Thevenin equivalent circuit from this terminal. The minus 4 plus J8 volt voltage source in series with 1 minus J ohm. Yeah. Okay. Then connected to the 1 ohm voltage here. So the voltage output here will be equals to the current, or you can use voltage divider formula, yeah? Or you can calculate first the current flowing through this circuit and then multiplying the current with this 1 ohm resistor to obtain V output. Yeah, this is using the V output here equals 1 minus 1 divided by 2J, 1 minus 4 plus 8J. I think, yeah, this is using voltage division formula. Yeah, minus 4 plus J8 multiplied by this 1 divided by this plus this, which is 2 minus J ohm. Okay, so then you obtain the voltage output here. Okay, now let's try to using Norton's theorem to solve the same circuit. To solve the same circuit, so first we have to calculate the I short circuit, the short circuit current across this resistor. So you put like this, and this we solve using node analysis. We make a super node here around the independent voltage source. So the I short circuit will be equals to from this node, the I short circuit equals to I triple dash X minus 4 ampere. So the I triple dash X equals to V3 minus this one is connected to ground, so the voltage here is 0. V3 minus 0 divided by 1 ohm. This is the Ix triple dash. The supernode constraint is V1 minus V3 equals to 12 volt, so similar to previous method of using node analysis. Then let's now using KCL at the supernode, V3 minus 0. This will be here, divided by 1 ohm, plus V3 minus 0 divided by J1 here, plus V3 minus V2 divided by 1 ohm, plus V1 minus V2 divided by minus J 1 ohm. Then here minus 4 ampere because this current flows into the node. Then KCL at V2 minus 2. Since this current is flowing into the node, so we assign negative value, minus 2 ix triple dash plus v2 minus v3 divided by 1 plus v2 minus v1 divided by minus j. The control variable here is I triple dash x equals to v3 divided by 1. From here, then we can obtain v1. So basically, we need to find the I triple dash x here. We want to find the IC. We need to find the ix triple dash. To find ix triple dash, we need to find v3, the voltage at node 3 here. Okay. So then we replace v1 using express v1 as a function of v3. Yeah, v1 equals to v3 plus 12. So that then we can replace this at the KCL at supernode. And from this KCL at v2, yeah, after multiplying this one with minus j, and we obtain 2j v3 minus j v2. So we replace already here ix triple dash with this controlling variable with v3 divided by 1 and multiplied by minus j becomes 2j v3 minus j v2 minus v3 plus, and this cancel each other, become v2 minus v1. And v1 we substitute using this equation, v3 plus 12. So this becomes v2 minus v3 minus 12 equals to 0. Okay. Then we simplify this further. We obtain 1 minus j v2 minus 1 minus 3j v3 equals to 12. So we still have v2 here. Yeah. So we use then the KCL at the supernode. Yeah, further. Okay, 1 plus j plus v3 yeah, plus from here j v3 minus j v2 minus v3 plus 12. So this one is from here plus v2 equals to 4j. Oh, I think from here. Then we simplify this, becomes 1 minus j v2, this and this one, plus 2j v3, this plus this is 2j v3, and then equals to 12, equals to 12 plus 4j. So from here, then we have two equations. The first one is this part, and the second one is this equation, both having two unknowns, v3 and v2. Yeah, by substituting and eliminating the v2 variable, we obtain 1 minus j v3 equals to 4j. So v3 value equals to 4j divided by 1 minus j. And hence the ix triple dash equals to this value divided by 1, or 4j divided by 1 minus j ampere. Yeah. Then ISC equals to ix triple dash here minus 4. This, yeah, this minus 4. Minus 4 plus 8j divided by 1 minus j. Multiplying with j and j, so we obtain here 8 plus 4j. I think this plus divided by 1 plus j with negative value here. Yeah, with negative value. Because this becomes negative 8. This becomes plus 4, negative 4j. Yeah, so there is a negative here. So from here, we obtain the ISC. The ZTH will be equals to the Thevenin equivalent resistance, the Thevenin equivalent impedance that we had calculated earlier, yeah, when we try to solve using Thevenin equivalent circuit. So from here, then we put this, the ISC minus 8 plus J4 divided by 1J ampere, and the ZTH. So this is to calculate the output, we need to calculate I output here, and we can use the current division formula. Yeah, current division formula. So 1 minus J divided by this plus this, 2 minus J multiplied by the current source. Yeah. Okay, so the solutions that obtain using node and loop methods in the earlier slides is this one, minus 8 plus 4j divided by 1 plus 2j. Okay, and using Thevenin's is here minus 4 plus hj divided by 2 minus j. So this is equivalent, yeah, basically if you multiply by j and j, for example, so this becomes 2j, this becomes positive 1, yeah, and the upper part, the denominator part, will become minus 8, yeah, this is minus 8, yeah, this one is minus 8, this part becomes minus 4j, yeah, this one minus 4j, so this is equivalent, okay, and this one is also, I think, similar, yeah, it's equivalent, but however, they are expressed quite differently. So here if you multiply this minus 8 plus 4j and divided by 1 plus 2j with 1 minus j and 1 minus j, at the numerator and denominator part, you will obtain this 12 minus 4j divided by 3 plus j. Okay, so yeah, be careful when you do this kind of questions. Yeah, of course, for me as the lecturer that will evaluate your answer, it will be easier if you simplify further from this, yeah, then multiply with a complex fraction like this. So to finally obtain the exact real part and the exact imaginary part. Yeah, because in this fraction form, yeah, it can be expressed in different ways, although they are equivalent answer. Okay, so we still have time. Yeah, for this first hour, let's try now another example. Compute the V output here. Okay, so we have this is one impedances in parallel. This minus j 1 ohm minus j 1 ohm in parallel with j 2 ohm in parallel with 1 ohm, and they are in series with 2 ohm, and they are connected with a independent voltage source 12 volt having a phase angle of 30 degrees. If you use nodal analysis, so this becomes a single node V1, yeah, V1 minus 12 here divided by 2, this current, V1 minus 0 divided by 1, V1 minus 0 divided by J 2 ohm, this part, V1 minus V output divided by minus J. So we still have two variable, V1 and V output. Solving for this node, the KCL at this node, V output minus 0 minus V1 divided by minus J plus V output minus 0 divided by 1 equals to 0. So from here, the relationship between V1 and V output equals to V1 equals to 1 minus J times V output. So this we can substitute into the first equation. We multiply first the first equation with 2J, yeah, so to eliminate this factor. So this becomes now this one, and then we substitute V1 here with 1 minus J V output. So this becomes this equation. Then we can solve for V output. If remember in the discussion about phasor section, it's easier if we have you usually use phasor in multiplication or division calculation like this one. Yeah, so it is easier when this multiplied by this, the value will be equals to 12 with a phase angle of 90 plus 30 degree. Okay, so with the phase angle of 12, with phase angle of 120 degree. So V output then is this value of multiplication divided by the value of this addition and multiplication, which is 4 plus 4j. How to simplify this? Yeah, of course, you need to re-express this 4 plus 4j into phasor form. Then you can do the division operation easily. Now, like this, into 5.66 with the phase angle of 45 degree. So the value will be 12 the magnitude is 12 divided by 5.66, which is equal to 2.12, and the phase angle is 120 minus 45, and it is 75 degrees. If we use Thevenin, then we need to simplify first, for example, between these two nodes, these two terminals, and then we can short circuit this independent voltage source. Then we obtain the impedance, the equivalent Thevenin impedance as 2 in parallel with 1 in parallel with J2. So we obtain this equivalent Thevenin impedance, or 4J divided by 2 plus 6J, or here 4J times 2 minus 6J divided by 40. The open circuit here, the open circuit, then we can calculate using voltage division formula. 1 parallel J2 divided by 2 plus 1 parallel J2 multiplied to 12 with the phase angle 30 degree. So we obtain this, and finally this is the simplified version. So we reconnect again the component, the 1 plus 1 minus J1 here into the Thevenin equivalent circuit. So the V output will be equals to 1 divided by ZTH plus 1 minus J1 times the V open circuit. Okay. Okay, so let's try here another approach of using mesh analysis. First we have done using nodal, then using Thevenin. Let's try using mesh analysis, but now for different circuit. This is the different circuit. With having a single one independent voltage source, one independent current source, and V output is being asked here. So we draw the two mesh circuits, I1 and I2. The constraint here then this current equals to I2 minus I1, right, from these two mesh currents. Then using a super mesh, encircling the outer loop, a super mesh or a loop, the outer loop of the circuit. Then we obtain minus 24 here, plus 2 ohm times I1. Then here minus 2J I2, times I2 plus 2 times I2 equals to 0. So here from here, then I1 equals to I2 minus 2J. Then we can substitute I1 using this equation. So this becomes this one, 2I2 minus 2J here, plus 2 minus, and we substitute here I1 with this one, I2 minus 2J, And from here, when we obtain the value of I2, from here we can obtain the value of I2, and the output is basically I2 times 2 ohm of the resistor, 2 times I2, 24 plus 4J times 2. This is 20. The I2 is here, 24 plus 2, 4J divided by 4 minus 2J here times 2, which is then 2 minus J. And then we express the numerator and denominator is as phasor form in the phasor format. So we obtain 24.33 with a phase angle 9.46 divided by 2.24 with a phase angle of minus 26.57 degrees. So hence we obtain 10.86 with a phase angle 56.03. Okay, if we use node analysis, here V1 minus 24 divided by 2, current flowing through here, minus 2 here, since this current is flowing into the node, so minus 2 with the ampere with a phase angle of 90 degree, plus V1 minus V output, divided by V1 minus 0, and divided by 2 ohm minus 2J. Okay. So from here, then we can, the formula for 2V output is a voltage division formula, 2 divided by 2 minus 2J times V1. Okay, so this is from here, from the first equation, then we can obtain V1. Then using this voltage division formula, we can calculate V output. Now using source superposition, first is we calculate the contribution of V output when from the independent voltage source only. So in this case, this one is disconnected, made to open circuit. So then V output due to the 24 voltage source can be calculated using voltage divider formula. 2 ohm divided by 2 plus 2 minus J2 times 24. Like this. The contribution from the current source is done by short circuiting this voltage source. Okay, then we can calculate using using current divider formula. Yeah, using current divider formula 2 times here 2 minus 2 times 2 divided by 4 minus 2J times 2 ampere with the phase angle of 90 degrees. Then the V output will be the superposition of the V output due to the voltage source and the one that is due to the current source. Okay. Another example, compute the V output here in this equation when using superposition. Now this is the same, like, well, no, not the same, because now this is a voltage source. Okay, if you use superposition, the contribution first from this voltage source, we short circuit first this first one. Then the second contribution due to the 24 volt voltage source is calculated by short circuiting the 12 volt voltage source. Okay, then the V output here will be equal to the V output dash plus V output double dash. So from here, then the V output here it can be calculated using voltage division formula. Yeah, the V1 here equals to 2 ohms parallel with 2 minus J2 minus minus 2J divided by this 2 parallel to minus 2J plus J2 here. Okay, times the minus 12 volt, minus 12 volt, because this is negative in the upper node. So from here, then after obtaining V1, then we can calculate V output dash here using voltage divider formula. 2 divided by 2 minus J2 times V1. With this one, to calculate the contribution from the 24 volt, so here we can see that V2 here can be calculated using voltage divider formula, which is 2J in parallel with 2 minus 2J divided by 2 plus 2J in parallel by 2 minus 2J. Then V output double dash equals to the, if we're using voltage divider formula, also 2 ohms divided by 2 minus 2J times V2. Okay, and V output, total V output equals to V output dash plus V output double dash. This plus this. Okay. Okay, so let's have a break for a while. Since sun is up, I will just stop recording for now.